I have a long list of collaborators that contributed to various parts of this. I highlighted Charlie here, who is on one of the examples at the end because he's around. He's got a poster here. He could use a job, maybe, too. He's fantastic. So yeah, that's Charlie. OK. So what I'm going to talk to you about is it's about Markov chain Monte Carlo, obviously. The goal in the end is simple. I want to make it faster. If you don't know, I think probably most of you know what Markov chain Monte Carlo is. I'll try and give it to you in a quick slide, just in case. But let me start with the real problem. So if I want to, where's the stick? OK, it's fine. Suppose I want to sample the density. Is that it? Oh, it is. OK. Suppose I want to sample. So this is I would call a potential. The density, the corresponding density would be pi. E to the minus is proportional to e to the minus v, okay? Which means it has a high likelihood point at A and a high likelihood point at B. I'm going to divide by this small parameter epsilon, which will be important later. All you need to know now is that if I take epsilon smaller and smaller, any standard scheme for sampling this distribution is going to be really, really expensive, exponentially expensive. How do you typically sample a distribution like this? Well, you construct a Markov chain whose invariant measure is pi. Okay? One example, the simplest example probably, would be just metropolis. So that's a symmetric metropolis. Okay? So hopefully that's vaguely familiar. Hopefully it feels about right that as epsilon goes to 0, the peaks, the two modes in pi, become sharp and tall. And it takes a really long time for this Markov process to jump from one to the other. And of course, if I haven't seen a jump from one to the other, I can't compute an average accurately if that average depends on, for example, seeing both basins. OK? So that's kind of the basic problem in the simplest version. In fact, we're also going to be interested in cases where maybe there's no transition, maybe there's no low probability region that the process has to transition through, but the quantity that you want to compute is a tail average. That's going to be important, too. And there the issue is just that, well, because it's a low probability set, if my Markov chain is doing the right thing, it's not going to spend much time there. And so again, if I want to compute that probability accurately, it's going to be expensive. Okay? So those are the kind of issues we're thinking about with the method that I'm going to tell you about. In our group, we're interested in both averages of this type. So you give me pi. You give me this density pi, like on the previous slide, and you say, and maybe a few functions, little f, objective functions, and you say, give me averages with respect to these objective functions. You don't care which Markov chain I build to solve the problem. You just want an estimate of these numbers. They could be probabilities. They could be whatever. There is another problem that and that's what I'm going to focus on today. There is another problem that we're really interested in, that we think about a lot, which is dynamical averages. So in this case, I'm writing one particular kind of dynamical average. But here, instead of you giving me pi, you give me a Markov process xt, and you say, I'm interested in averages with respect to that particular Markov process. Okay? If you use a different Markov process, you've got to fix it somehow so that the statistics you generate are for the Markov process that I gave you. Okay? So that's a little bit of a different perspective. I'm not going to spend, so the example there would be for, I want to know what's the probability of forming a large hurricane from this particular initial condition within a particular amount of time. Okay, so there I'm dealing with the weather. I don't get to change the Markov process. Okay, but I'm going to spend time in this talk really focused on what I would call these static averages. Okay, so here's the basic idea, and it's an old philosophy, really. I mean, in statistics, stratification, you may know, is over 100 years old. It's a really ancient idea in statistics. And even in computational statistical mechanics, it's pretty old. So people have been doing what I'm going to show you, exploiting this basic philosophy since the late 70s. It was really, I think, the first example where they really use it in the same way that we're using it here was this paper from 1979. Okay? And here's the basic idea. So the first thing, let's imagine that the problem is one-dimensional for a second. Then I'll get to higher dimensions in a second on the next slide. But suppose it's a one-dimensional problem like that double well I just showed you. what I'm going to do is introduce a bunch of bias functions. So these are just non-negative functions. I'll assume that they sum to 1. In most of my examples, they're going to decay quickly away from some point. So imagine that I lay down a grid of points in this 1D direction. And then each of these is centered at one of those points. Maybe think of Gaussians or something. They wouldn't sum to 1, but you could fix that. Gaussians that decay quickly away from that center point. Okay? So these are my bias functions. I'm going to define restrained distributions, which are just take pi and multiply by the ith bias function. That gives me the ith restrained distribution. So now it has some characteristics of pi, but psi I is going to make pi I decay quickly away from the ith center point. Okay? Then I'll define these normalization constants, just the integral of psi I with respect to pi. The final step is if I have these normalization constants, you'll notice that here, because the psi I sum to 1, I can assemble the average that I was hoping for in terms of averages with respect to the pi I. OK, so the assumption was that any average with respect to pi is going to be is too hard to compute by my favorite Markov chain Monte Carlo method. So I've written the average. If I knew the z's, hold on a second on those. If I knew the z's, I've written the average that I wanted to compute, which was an average with respect to pi, in terms of averages with respect to the pi I. Okay? Now, for this to work, those averages with respect to the pi I have to be easier to sample than averages with respect to pi. Okay? And it turns out that can be arranged. That's going to be the story later. Okay? That assembling all of these guys, and I have to assemble a few more averages with respect to pi I, actually, but computing averages with respect to pi I is going to be much easier in some cases than computing averages with respect to pi. Okay? And you'll see that in the right situations, you can get really massive speedups. And again, I mean, I'm not listing the applications papers. These are the papers where this kind of philosophy in a computational setting first appeared. But then there's tons of papers where this basic philosophy has been applied with great success in chemical physics. OK, so my goal is not really to introduce a new scheme. It will be a slightly new version of this philosophy, but it's really to understand it and come up with some useful tools that can be used in conjunction with it. OK? So so there's an obvious issue here, which is that the z's are an integral with respect to pi. And I just said the assumption is I can't compute integrals with respect to pi. OK? So that's an issue. I'll take care of it in 1 second. Before I do, the other thing I said was that imagine that you have a 1D problem. All those examples that I mentioned are obviously not in 1D. They're in many, many D. And I'll show you examples at the end. They're in many, many D. So what you have to do, since this is a gridding-based scheme, you can't grid many, many D. So what you have to do is come up with some kind of what's usually called a collective variable. So it's some low-dimensional, possibly nonlinear projection of your high-dimensional problem into 1 or 2 or maybe 3 dimensions, which you'll then grid. And somehow that projection has to capture, so this is very close to basically Tony talked about this for a half hour the other day. So it's very close to what he was calling the concept of reaction coordinates. So you want the other directions, the other variables that aren't represented by this function theta to be easy to sample. So conditioned on the value of theta, the conditional distribution is easy to sample. That's the rule of thumb. Yeah?
Could you go back to this slide?
The previous slide?
Yes.
Sure.
There is an expansion called Edwards expansion.
Oh, Ewald expansion? Yeah. So this is totally separate thing, not related to that.
So it's not applicable here. Like you cannot use that.
Well, you might use it within your Markov chain Monte Carlo algorithm. It might be something that appears, but no. This is I mean, in fact, everything the algorithm that I'm going to give you is exact. I mean, exact in the sense that you get a consistent estimator, even if you do something very stupid. So there's no approximation going on. No clever approximation. OK? OK, let me also mention that I'll show you an example where instead of gridding instead of this reaction coordinate idea, we do something that's very typical in statistics and also in chemical physics, which is to temper. So you can define these bias functions psi j so that the restrained distributions are actually just tempered distributions. And there are reasons to do that. So pi to the power less than 1, which should be easier to sample than pi. Okay? There are reasons to do that, which I'll maybe mention when I get to an example of it. OK, so let me give you but still holding on the how do I compute the z's, let me give you an example, a toy example of how, oh, that didn't render very well, but a toy example of how this scheme is typically used. So this is a very small toy molecule. It's 66 degrees, and this is actually done in vacuum, so it really is small. In this example, people basically know that there's these two angles, the phi and psi angles, that if I plot the marginal in those two angles, I basically understand what's difficult about sampling the full distribution of this, the full canonical distribution for this small molecule. And so this is a plot of that marginal. You can see that there's a well here, a high probability region here, a high probability region here. And to get between them, you have to go through these barrier regions, TS, transition state 1 and transition state 2. It's periodic. These are angles, so you can come around. OK, so this is just an example of when I mentioned all those papers, the kind of things they typically do. So here, I would actually have many objective functions. Each one might be like a function that is 1 on a little square and 0 everywhere else, so that I build essentially a histogram representation of my marginal distribution. Okay? In this case, this is done using umbrella sampling where we grid these two angles. Okay? But actually, the dimension is there's 66 dimensions in the full problem. Okay? So that's a typical kind of application of this umbrella sampling idea. OK, so back to the z's. So how can I represent the z's as, instead of averages with respect to pi, as averages with respect to the pi I? So I can completely forget about pi. And that's just the same formula I had for f. So this was the expression for f in terms of averages with respect to pi I, which means that if I plug in psi j for f, I get a formula for zj. OK, but zj appears on both sides, so actually, this is an eigenequation. It's an eigenequation with this matrix F, which happens to be rho stochastic, because I've assumed that in the way I've described it, I've assumed that the psi j is summed to 1. So this has rows that sum to 1 and non-negative entries. Okay, it's a stochastic matrix. So it has a dominant eigenvalue of 1, and z is the corresponding eigenvector. Okay, so what does that mean? That means what I'm going to do after choosing my restraining functions and using them to define my biasing functions, I'm going to go use my favorite MCMC scheme to sample each of the pi I. OK, whatever scheme you like, whatever's your favorite. I'm going to compute all of these averages f that appeared in the expansion, these averages of f with respect to the pi I that appeared in the expansion of the average of f with respect to pi. And I'm also going to compute all the entries in f. OK, so those are all a zillion averages I have to do with respect to the pi I. So that's, unfortunately, I have to do many, many averages. The good news is that, well, many of those averages can be used, so all the averages in here can be used for any objective function, but also the sampling with respect to the pi I can be done in parallel. OK, it can be done in parallel. In fact, typically it's not quite done in parallel, but it's pretty much in parallel. OK. So then you solve the eigenproblem for z, and then you assemble. OK, and that's your estimator. OK. So like I said, this is not quite the way it was described in the past, but the philosophy is absolutely an old philosophy. We've simplified it a little bit relative to other descriptions because we want to be able to say something about why this thing works. There were descriptions of why it worked in the chemical physics literature, but they were incomplete. And I'll tell you how they were incomplete in a second. Okay? So we really wanted to understand, why has this been such a successful scheme? What's going on? So let me mention, not only is it simpler, but actually it's really just about as accurate. In fact, you can turn the estimator that I just gave you into an iterative scheme that at convergence would give you something called the M-bar estimator, or it's called the M-bar estimator in chemical physics, which is a pretty popular estimator, not as popular as another one called WAM, but you can see they all basically give very, very similar results. In fact, this M-bar estimator was used in statistics or discussed in statistics in the context of computing Bayes factors, so normalization constants for different models. So there the idea was completely different. I have these different models. Those are my pi i's. I'm not designing the pi i's to sample from something pi. There is no thing pi. I have separate pi i's, and I want to know their relative normalization constants. So the same mathematical formulas that I described appeared in that context in statistics from this guy, Vardy, and he studied them quite a bit. And let me also mention that this umbrella sampling philosophy is also very close to this work that Scott Schmidler did, which appears on the archives from 2013. OK? So here I'm mentioning the iterative version of this scheme. OK. So that's the algorithm and how it relates to what came before. I said what we really wanted to do was understand why this thing works. So step one in understanding why it worked was coming up with a general error bound. So this is a bound on the asymptotic variance of the scheme. Okay? So we assume that your sampling schemes for pi I all have some asymptotic variance. So for each pi I, you have a sampling scheme which for a given observable has a given asymptotic variance. And we say, how does that translate to, first of all, a central limit theorem for the algorithm, and second, a bound on its asymptotic variance. The bound on the asymptotic variance I won't go too carefully through. I will just use it to show you some consequences. But let me say that it breaks into two pieces. One has to do with the error in the entries in F, and one has to do with the error in the local averages you compute over F. The errors in the entry of capital F, the matrix, and then the error in the average of little f with respect to pi I. Okay, so this is the little f with respect to pi I, and this is the consequence of errors that you make in the entries of F. Okay.
So this is for Markov chain Monte Carlo techniques to approximate the pi i's, or it's like
so all the
IID, or?
So all no IID. Sorry, not IID. Not IID. The first thing. The first thing. Oh God, the first thing. Yeah, yeah. It's so what goes. That's what I was saying. What goes in here is some assumption about the asymptotic variance of your underlying pi I scheme on pi I. Okay. So you have to understand. Can this umbrella sampling scheme? I mean, that's the first thing to understand, and that was definitely understood by chemists. That was their whole intuition, was that if I choose these psi correctly, then I can, maybe my original problem had a very long autocorrelation time, a very slow mixing time for pi. But when I localize, I can get a much faster mixing time. So that is one component in understanding why the scheme works. Okay? Okay. So, so there's, like I was saying, there's really two parts. You need to understand, well, what are my errors in F in the matrix entries and in the averages of little f with respect to the pi I. And like I said, it was understood that somehow by localizing I can make these errors smaller for the same amount of work. Okay. What didn't appear, at least in the explanations, and why actually it led to it could lead to, if taken too literally, to some wrong conclusions, is that, well, you also have to think about how errors in the entry in F propagate through the eigenproblem. It's very possible that you make a small error in the entry of F, and that balloons into a huge error in the ZI, especially for the kind of problems we're looking at, these multimodal problems where the original Markov chain had a small spectral gap. I'm not going to go into why, but basically anytime the original Markov chain has a small spectral gap, you'd expect this matrix F to have a small spectral gap. Okay? So this is another piece of the question that you have to think about. I'm going to start with the second part, So really, what is that? That's, what time am I done, by the way?
Well, with questions, so maybe 5 after.
Okay. So that is a question a lot of people have asked for a long time. I have totally outside the context of Markov chain Monte Carlo, of course. I have, or umbrella sampling. I have a Markov matrix. I have errors in the matrix. How does that translate into errors in the dominant eigenvalue? A very classical problem. Lots of people have thought about this. Here's a list, circa 2001, of papers with bounds. All those bounds are of this type. Okay? So some norm on the error in F times some constant bounds some norm on the error in Z. I won't specify the norms because it differs by paper. But basically what you see is that this is just two of the constants, the blue and the green. This is for a particular example where the spectral gap is decreasing. Okay? The spectral gap is decreasing as I increase the size of the matrix. And what you're seeing is those bounds blowing up. Okay? In fact, all of these bounds, whoops, I guess I removed that slide. All of these bounds, for all of these bounds, these constants behave like 1 over the spectral gap. So if I have a matrix with small spectral gap, exactly the kind of matrix I'm expecting to have, these constants are going to be enormous. In fact, if I take that original problem where I was sampling e to the minus v over epsilon, remember I said that that becomes exponentially expensive for Markov chain Monte Carlo as epsilon gets small. If I take that problem, these spectral gaps will blow up exponentially. These bounds will blow up exponentially. So even if I've saved some effort in the sampling of each pi I, even if this intuition that sampling pi I is fast, even if that's true, it's all thrown away when I solve the eigenproblem, because I make a small error and it gets blown up. I need to make those errors exponentially small. Okay? So the first thing we had to do was just go back to this problem and come up with a more detailed bound. So a bound that takes into account really the kind of perturbations that are typically made in umbrella sampling. So this is a bit of a complicated bound, but let me just point out that, first of all, there should only be one bar there. This is a measure of the relative accuracy in the z's, in the entries of the eigenvector. That's important because, like I said, we're interested in a lot of times we're interested in small probabilities. It's not enough to just have absolute accuracy. This is relative accuracy because it's difference of the logs. Okay? Over here, if I ignore the gammas, what this bound says is that the relative accuracy in the entries of Z are bounded by the relative accuracy in the entries of F. No other structural constant like a spectral gap. Okay? Just bounded. So in fact, it's a corollary of this that I can remove these gammas. So what that would say is that, that I get, if I have relative accuracy in the entries of F, I'm going to get relative accuracy in the entries of Z. Okay, which is good. Now, these gammas, I won't get into them, but they basically say, well, actually, you don't need relative accuracy in all the entries. Here's how much accuracy you need. Okay? And these are all computable. In fact, they're computable in the same, all these numbers are computable in the same amount of effort that it would take to compute Z, n cubed. Okay, so it's really no more work. You do have to be a little bit careful about how you do it when the matrix has a small spectral gap. Okay, so that was important. And it's really responsible for what's going on in this example. So here I want to draw a conclusion. I gave you the general error bound. I want to draw a conclusion from that general error bound that suggests that this is a good idea. This umbrella sampling scheme is a good idea. So what am I going to do? I'm going to look at another exponentially difficult problem. So suppose that this random variable x has exponential tails, and compute and ask how would you estimate the probability that x is beyond some level m. Okay, that's going to be exponentially expensive by any direct method. Even this actually has nothing to do with the autocorrelation time. Even if you use independent sampling, this is going to be exponentially expensive to get with relative accuracy, right? Because you'll just never get samples out there. Okay, so you can do something pretty naive and just basically a uniform grid of the variable. So whatever variable you want the tail of, in this case the variable x. You can do a uniform grid work out how much effort it would be to compute the entries of the matrix with relative accuracy, or the entries that matter. In this case, there are no. This would be a tridiagonal matrix. So if you think about the entries in F, where the integral of psi I with respect to the integral of psi j with respect to pi I. So that only if 1 and 4 don't have overlapping support, then that entry is 0. So for this particular matrix, the way I've set it up, it's tridiagonal. Okay? And those tridiagonal entries can be kept relatively large. If I have large entry, getting them with relative accuracy is not hard. Okay? And so, so I can get these entries with good relative accuracy. It means that I've gone from an exponentially expensive problem down to an algebraically expensive problem, okay, in epsilon. Sorry, in M. So as M increases, the direct method, any direct method, would be exponentially expensive for relative accuracy. For umbrella sampling, even with this simple discretization, it drops down from exponential to algebraic. Okay? So that's one demonstration of the utility of this umbrella sampling idea in the context of sampling tails. Now, back to the double well picture. So the idea in the double well picture is, look, take a strip, take a narrow strip, and take psi I to be, I mean, just imagine that the psi I here is this strip. So it's 1 on the strip and 0 off the strip. Okay? Let's look at the conditional distribution within that strip. And what you see is that you get something relatively flat. So there's no, which is intuitively clear. You don't get any big low probability regions you have to cross. All the issues that made pi hard to sample are gone when I concentrate on this narrow strip. And in fact, and so here's a narrower strip. You see it gets even smoother. And so, in fact, if I make a specific decision about what schema I'm going to use, so if it's a strip like this, I might imagine that I'm going to use reflected over damped Langevin, just as an example scheme. You could use whatever you want. The results would be similar. You would get a bound, for that scheme, you'd get a bound on its asymptotic variance within the strip. So I'm using reflected Langevin within the strip. I get a bound on its asymptotic variance of this type. What's important here is that you see that as I narrow the strip, so even when, so sorry, beta is 1 over epsilon. Sorry. Even when beta is really big, when epsilon is really small, this thing that I get to control appears multiplying the beta, not multiplied by e to the something involving beta. So I can keep this term moderate even as beta goes to 0 just by making this scale like 1 over beta. Okay? Which obviously increases the amount of work. It means more of these windows, but like 1 over beta, rather than like e to the beta. Okay? What's that?
You say beta 0, it's beta infinity.
You're right. Yeah, beta getting big, epsilon getting 0, going to 0. I should switch that for epsilon. Okay, so that's the idea. The cost within these strips scales like 1 over. Sorry, you can control the cost within the strip by scaling the strip like 1 over beta. Okay, let's see. So and then the same comments about the entries of F that I made on the previous slide would basically apply in this slide as well. If I choose these windows to be overlapping and narrow, but overlapping by an amount that's substantial, so not allowing the overlap to go to 0, then I'm going to get a matrix that's basically tridiagonal. The entries on the tridiagonal are going to be relatively large. If the sampling of pi I is not slow in the sense that its autocorrelation time is not too big, then it'll be low cost to get all those entries with relative accuracy. Okay? That's the story in a quick summary. Okay, so I want to get to some examples, but this is not the example, but let me show you a utility of this kind of thing. So we have that general error bound, and it's, like I said, it's very computable. What can you do with it? Well, suppose I've done some umbrella sampling on this alanine dipeptide. I can ask, OK, well, which of those pi I, so again, this is a 2D grid of pi i's, which of those restrained distributions caused me the most trouble, contributed the most to my error, my final error of the entries of F? So in this case, I think this plot corresponds to an objective function of just the ratio of these two, the probability near here and the probability near here. This plot would change if I change the objective function. But for any objective function, I can ask which of my windows windows is what I call the pi i's. Okay? Which of my windows is contributing the most to the error? That can be because the sampling was slow in that window, or it can be because of what's going on in the error bound, the contribution from the matrix entries. So I have matrix entries. The errors in the matrix entries may not be that big, but the matrix entry may be really important to the eigenproblem, meaning that small errors in that matrix entry just get amplified a lot. Okay? So you can get a picture like this, which is, you could maybe look at it and try and learn some interesting things. But at the very least, you can think about how to allocate the rest of your resources as you go forward with your umbrella sampling. And that's something we've done on much more complicated problems now. OK, I left this one first. This video doesn't play when it's in PDF, but it's not that exciting. This is dissociation of two human insulin monomers. If I played, this is actually at 360 Kelvin, so we're cooking them, and running them for a zillion steps, 10 to the 8 steps, and all you'll see is they sit next to each other and shake. And what we're actually interested in is them coming apart. Okay? So you can't do that by direct simulation, even if you raise the temperature. If I raise the temperature much more, I start to get garbage. I'll cut the story short, but I do want to dispel so some people who know about these rare event simulation schemes but don't come from chemical physics. I often hear, well, in chemical physics, you have these reaction coordinates all over the place. They're just handed to you. It's easy. It's not easy for a hard problem to find a reaction coordinate that works. It took a lot of work to find reaction coordinates for this problem. But you do have to be willing to invest in your problem in some cases. Okay? So I mentioned the tail case, the case of tail probabilities. That's an important exception in the sense that if I want to compute the tail probability for variable blah, I'll discretize variable blah. There's sort of a natural choice. But for these multimodal problems, there's not usually a natural choice. You have to really want to solve that problem. Okay? And you have to think about it and try things and eventually come up with something that works. Okay? I mean, this is the reaction coordinate discussion.
So how you go from the string to
So we did lots and lots of strings, lots of computing time with the strings, and then we start filling. Then we decided we use those to decide on these two dimensions, just by looking at them and looking at the structures, and then we start pulling off of these to fill this plane.
So by pulling off them, you run for a while, and when it leaves,
Yeah.
you put a new
So
box.
we are in the course of running the string. We already have trajectories here. We would pick one of those points, run a trajectory here with the next restraint. So there's 700 in the end. The plot that I'm going to show you, this is the free energy plot. Actually, as of a few months ago, I think it's gotten better, but there's 700 windows in this plot. So there is still an enormous amount of computing time that went into this plot, and that was a few months ago. So here we're using the error bounds to show what the errors look like. Again, this was a bit early, so we don't have great pictures here, but it does allow us, and we did use this to go focus in on areas to sample a lot more. So we didn't, after generating this plot, just go sample all 700 windows again. We went back and said, these are the windows we need to sharpen up. Okay? OK. So now let me, in just a couple minutes, go through this cosmological problem. So we're working, this is with Andrei Kresov, who is at U of C. Charlie really did all the work here. And Elise Jennings, who is at Argonne, right, Charlie? Who's at Argonne? So Andrei was interested in, so these are two parameters. These are the mean dimensionless matter and vacuum energy density. This whole thing, so there are 6 parameters that really matter, but if I want to do posterior in the model, but if I want to do posterior estimation given some likelihood, in this case it's a likelihood from supernova data, if I want to do posterior estimation, I need a bunch of latent variables. The whole thing ends up being, I think, 12 at most, and that's how many were in here as well? OK. The whole thing ends up being about 12 coordinates. So what Andrei was interested in was looking at the tails in this two-dimensional plot. So these two particular numbers, the mean dimensionless matter and the vacuum energy density. OK, we tried two schemes. So he was particularly interested in this tail, OK, the tail going this way. And I'll show you why in a second. He's particularly interested in this tail. And so Charlie tried two things. One was, well, the obvious here. I want to go in this direction. Look at this tail. I'll just discretize this coordinate. Chop, 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 chop. I get a bunch of strips. I sample within those strips. Those are my windows. OK? That was one choice of collective variable. Then the other thing he did was this tempering version, which actually is a great way to combine data from from simulations at different temperatures. It's much better than a lot of naive schemes that actually give you worse results than just direct sampling. So the question was, in this case, can this tempering thing compete with the collective variable approach, and how do they both compare with direct simulation? Okay? The reason he cared about that tail was that if you look below this dotted line, which is, so this is slope a half. If you look below this dotted line, you get parameters or values corresponding to decelerating expansion of the universe. Okay? So around 2000, there was a paper that confirmed that the universe was expanding. And then, what's the story? And then in 2015, someone said, well, maybe the probability of deceleration is a bit higher than we thought. Okay? And so we wanted to, this is a tail, the probability of deceleration is quite small. It's a tail probability. We wanted to get it more accurately. And so, well, so we used our algorithm here. And what you find, yeah, is that it's a fairly small probability, 10 to the minus 7 if you don't put any constraints on this omega m parameter. It turns out they have reason to believe that actually they have strong reason to believe from other data that omega m is always bigger than 0.2. That, since this corner of the triangle is the most likely, that actually chops quite a bit of probability from the probability of deceleration, and we get much smaller numbers, which using a direct MCMC scheme you just can't compute. So here's the error without this restraint, this constraint, the omega m greater than 0.2. Okay. So in the end, I have to say that Andre became less and less enamored with the likelihood function. So he found some problems in the likelihood function that the people used that we were comparing to. So they had used a different likelihood, and then they had done a Gaussian approximation. Well, some people had used a different likelihood. Some people had used Gaussian approximations. We chose one of these likelihoods, and we actually did the sampling and computed the numbers. We got different answers from both. But in the end, he decided that neither of these likelihoods, they both had problems, and they both, so he wasn't really satisfied with saying that we had said something really important about this probability in the end, unfortunately. So some work needs to be done on the actual likelihoods. But the point is that the method itself can be a useful method. So but to put a little bit of a qualifier on the final results. OK, and that's the last slide.